In the last class, we had discussed cache memory and cache memory arrangements. Today, we shall look at virtual memory and how we can use virtual memory in an embedded system. The basic motivation for having virtual memory to use physical DRAM like a cache for the secondary storage. The secondary storage in case of embedded system can be a disk or maybe even flash memory being used as a disk. So what is required is that address space of a process can exceed the physical memory size when we are using virtual memory. So I may have the DRAM or SDRAM not occupying completely the address space, maybe occupying part of the address space, and I may have secondary storage which may be flash or maybe disk, and I can use the addresses in the secondary memory for realization of a memory space bigger than that what is available in terms of SDRAM on the embedded system. The virtual memory also simplifies the memory management system, because when I'm having a multitasking OS, and particularly in an embedded system when I need to deal with multiple concurrent tasks as demanded by the physical environment, I need to have these tasks active in the embedded system itself. So I need to manage the memory spaces of these different processes. So each process will have its own address space. Now a virtual memory system enables us to manage the processes. Processes are programs in execution in its own address space. Effectively, only active code and data is actually made resident in the main memory or DRAM. So you can actually allocate more memory to the process as needed. Non-active code, that is code belonging to the process which currently non-active, may be resident in the secondary storage, and when they become active can be brought into the main memory which is your DRAM. So effectively DRAM is functioning as a cache with respect to secondary storage when you are using virtual memory. But another very important property is provided through virtual memory is that of protection. One process should not interfere with another process because they operate in different address spaces. These we can make sure once we have implemented virtual memory, because then we shall have a clear partitioning of the address space of different processes. Further, user process cannot access privileged information because different sections of address spaces can have different permissions. This is particularly important to have an enhanced security feature on our embedded systems. Today, we have got embedded systems which can download code and execute on it. So this downloaded code available from variety of sources should not corrupt the actual software which is running the embedded appliance. In order to ensure that protection, virtual memory is important. How is virtual memory realized? Using primarily memory management unit. This is provided with many of these modern microcontrollers which are targeted for use in embedded applications. So memory management unit provides the key service of managing tasks as independent programs are running in their own private space. MMU simplifies programming of application tasks by providing resources for managing virtual memory. MMU translates the addresses, the logical addresses the programs generate, to physically moving around the code. So, conceptually, memory management unit lies between the CPU and main memory. When an instruction is executed, the addresses that CPU generates for accessing instructions or data are logical addresses. These logical addresses are received by the memory management unit, and this memory management unit translates this logical address to physical address, and these physical addresses are addresses of the main memory locations, from where the instructions or data are actually fetched. Now, how is this virtual memory realized? The simplest form is that of a segmentation based memory organization. Whether we are having really the mapping from secondary storage to the primary storage or not, independent of that fact, I can have my primary memory organized in terms of segments. This segmentation is primarily provided by the simple MMU. In fact, you are familiar with 8086. 8086 makes use of, in its program, a program running on 8086 can make use of 4 logical segments: data segment, code segment, extra segment, stack segment. The segmentation based memory organization that we are discussing now is a simple extension of that basic concept. So, program views its memory as set of segments: code segment, data segment, stack segment. Each program has its own set of private segments. So, this clearly defines different addressing space for different processes. Each access to memory is via what we call a segment selector and an offset within the segment. Now, all these things permits a program to have what we are already telling, to have its own private view of memory and to exist transparently with other programs in the same memory space. Obviously, what is implied by this statement that a program which is in execution will not access a data segment which belongs to some other process or program in execution. Now, the whole infrastructure which is provided by the MMU will ensure that such accesses are really denied, and if any such access attempt is made, an error is flagged. So, the address generation is through this process. So, in fact, the address actually can be divided into 2 parts. The address which the CPU generates can be logically looked at consisting of 2 parts. The first part is segment selector, which actually indicates the segment. The other part is a logical address, which is really an offset in the segment. Now, this segment selected is used to access the base address of the segment in what we call segment descriptor table. So, this gives me the starting point of the segment. So, using the segment selector, the starting point is obtained from this table. That starting point is added with the offset to get the physical address. This is the address using which a location is accessed in the primary memory like DRAM or SDRAM. So, base is the base address of the segment. the logical address is offset within the segment. And the next thing which is to be noted is a bound, because each segment can be associated with a fixed size. So, this bound information can also be kept in the segment descriptor table. So, what is checked is that once we do this sum, that is offset with the base, that should not exceed the bound of the segment. If it exceeds the bound of the segment, then there will be an access fault. So, this is an exception. We had earlier discussed interrupts and exception. This is a internally generated exception which is to be handled by the operating system. So, this mechanism ensures that each segment is clearly separated out and you cannot access beyond the segment boundary. The next form or the next way to implement virtual memory is by use of what is called paging. Now, the core concept is logical memory area can be bigger than the physical memory. In fact, this is one of the motivations with which we started on the concept of virtual memory. Logical memory can be accommodated in the secondary storage, and what can be done is divide physical memory into equal sized chunks, and these chunks are really pages. Any chunk of virtual memory is assigned to any chunk of physical memory, and that is the basic principle of paging for implementation of virtual memory. So, what can be inferred from this? Let us say I have a pretty large secondary storage. The secondary storage is also logically being divided in terms of chunks or pages, and I have space for few pages in the primary memory, and depending on which process is currently active, pages from secondary memory will be loaded into pages of the primary memory. In fact, conceptually this is very similar to that of cache blocks. You map memory locations to cache blocks. This is exactly what is happening, but here now we are talking about the secondary storage and SDRAM or DRAM interaction. The difference between segmentation and paging is what? Segmentation can be of arbitrary length. Here when we are talking about pages, we are talking about chunks of fixed length. So, pictorially the process is like this. CPU generates the logical or virtual address. We use this logical or virtual address to map into what we call a page table. This page table is representation of the storage area required by a process. So, a process occupies memory area. So, that memory is divided into a number of pages. Okay. So, here we are talking about P pages for a process P. So, a process is divided into P pages, and all information about all these pages are to be maintained in a page table. So, there are P entries in this page table. Now, all these pages belonging to a process are not necessarily resident in the physical memory. Some of the pages are resident in physical memory. So, here we are showing one example. This page is resident in physical memory at this location, because memory is also logically divided into pages. And another important thing to be noted, these pages can be accommodated anywhere in the memory. So, therefore, pages need not be stored at contiguous locations in memory. Some of the pages which are not in the physical memory can be resident in the additional storage or the secondary memory. This additional storage can be disk. In fact, for a general purpose computer system, it is invariably a disk. For an embedded system, it can be a disk or it can be a flash memory area. In fact, the hardware which manages the page table converts these virtual addresses to physical addresses, and this page table, the software wise, this page table, what will be the mapping or the entries in the page table is managed by the operating system. So, operating system actually knows where the pages are getting mapped to physical memory, and accordingly it will load the addresses in this page table. So, what happens when CPU generates an address of a page which is not in page table? Then we have what we call page faults. So, page faults occur when CPU generates an address which is not in memory. So, page table entry indicates that virtual address is currently not in memory. So, this is a memory exception. Okay. So, this exception handler is invoked to move data from disk or other secondary storage into memory. In fact, if you remember that ARM has also got a corresponding exception and the corresponding mode to handle these kind of exceptions. So, current process which generated this request cannot execute. So, it has to be suspended. But since we are talking about a multitasking system, there will be other active process in the system. So, that can now be resumed and executed. In fact, OS manages this. So, what we have, the OS also has a full control over the placement, that is where the pages are to be obtained and where they are to be mapped. So, what happens is that when the page fault exception occurs, so that data from the disk is fetched, okay, that page, what we fetch at a given point in time, a page. Again, the same principle that we had discussed in the context of cache, that temporal and spatial locality is exploited. So, I do not fetch a single instruction, but I fetch a page, and that is put in the memory. So, the exact servicing sequence, if we want to look at it in terms of these hardware operations, so what really happens? So, processor signals the controller which provides a read block of length p starting at disk address x and stored starting at memory address y. So, this is the action which is actually taken care by the exception handler, because this is what is told to the controller, that is your IO controller which is managing the disk. Here I am just illustrating it with reference to the disk. It can be also with reference to a flash controller or flash interface. Then the IO controller takes the data from the disk, and then once the data has been obtained, a DMA, direct memory access, is requested. This direct memory access is executed under the control of IO controller. So, from the IO controller buffer actually, which in a way logically from the disk, the data goes into the appropriate location in the memory. In fact, where it will go into the memory is provided by the exception handler. Once the DMA is over, the IO controller interrupts the processor. It generates an interrupt telling the DMA process is complete. So, once the DMA process is complete, now the page is in memory. So, the process which was suspended because it generated a page fault exception can now be resumed. Resuming means what? It can be put into an active or ready queue. So, when there are multiple processes, what happens with this page table? I have already told you that each process has its own virtual address space. An operating system controls how virtual pages are assigned to physical memory. So, the simplest way to implement this is that each process will have its own page table. In fact, under that condition, every program can actually start at the same address, same virtual address. But where that same virtual address is getting mapped onto the physical memory, that information is contained in the page table. And the process should not access pages not allocated to it. So, all the protection information now will be associated with the pages. So, for each process I shall have its own page table, and there would be permissions associated with the pages, and the permissions would ensure protection of the code in the embedded system. So, the pictorially it looks like this, that process, this is process I and this is process J. So, each of it, these processes have their own virtual page tables. Okay. Now, what we have shown here is a kind of a permission information. It can be much more elaborate, but here it is showing that read, write, where the process I has got a read permission for this page, because this is virtual page 0, this is getting mapped onto a page 9 in the physical memory, and it tells that this process I, whether it has got the permission to write onto this page. It does not have a permission to write onto the page, but it can read from that page. BP1, for this page it has got the permission to both read as well as write. Similar thing would be true for process J. Now, you can understand this enables also sharing of pages across processes. So, if I have a library routine or a common routine or a procedure which is to be used by more than one process, I can keep it resident in a physical address space, and for that physical address page I shall give read permission to all the processes that need that page, but I shall not provide write permission to any one of them. In fact, typically a code page, even if it is a private to a particular process, that page containing your code typically does not have write permission. Only the data area, the pages corresponding to the data area do have write permissions. The other point you should keep in mind is that obviously when I am executing a process has got logically a code area, it will have an area for store the globals, it will have the stack to accommodate local variables as well as the return addresses for subroutine calls. It will also have heap to accommodate dynamically allocated storages, that is the storages that you allocate for implementation of linked list. Now, all these are different logical memory areas that are required by a process to execute, and all these memory areas are again divided into pages, the chunks. So, when we are looking at pages like segmentation system, we do not talk about logical code segment, data segment, etc. We talk about the pages which belong to a process, but these pages can have logical relevance in terms of, that is, they can have code, they can have data, that is, they can actually implement the stack, they are part of the stack of the process, they can be part of the heap for the process. Now, how is the page address really translated? The basic principle is same as that of the segmentation. So, you have a page. So, now we look at the address which is being generated, the logical address which is being generated by the CPU as combination of page and offset. So, this page number is mapped onto a page table that provides the base of the ith page. If I have this I as a page index, it would provide the base of the ith page, and that base is concatenated with the offset to access the exact location in the page. So, I can have a logical address and the corresponding page can be located anywhere in the memory. What I need to have actually the page table appropriately updated. So, in more detailed form, we have this kind of a structure. So, this is my address, the virtual address or the logical address. I have a virtual page number. Okay. This is part of the logical address. This is the page offset. I use this virtual page number to access a location in a page table. Now, there is a page table base register. Now, you can understand that when I switch from one process to another process, my page table would change because each process has got its own page table. So, changing page table would essentially imply changing page table base register value. So, the virtual page number is like an offset added to the content of page table base register to access the location in the page table which has got the physical page number. But in the corresponding entry in the page table, please note that along with physical page number, we have other informations as well. We have a flag called valid flag, which says that if valid is 0, then page is not in memory. Therefore, conceptually this is same as that of your valid bit in your cache. Then there are few bits which are used for defining the access permissions. In fact, what we have not also shown is the dirty bit, because if I have write permission for that page, then the process can actually update content of that page in the memory. So, when it has to be stored back to the secondary storage, if that page is evicted from the memory, I need to write it back. So, I need to know whether content of that page has been modified or not. So, dirty bit would flag that condition. So, here you have the physical page number and the page offset added to it will give you the actual location in the page corresponding to a logical or virtual address generated by a CPU. In majority of the modern microcontrollers which are used, the MMUs support paged memory and page table associated with individual processes. So, what are the therefore operations of page table? The basic operation of the page table is translation, because you have separate set of page tables per process, okay? And we have already seen that virtual page number forms index into page table. That means it points to a particular page table entry. And then you compute the physical address. So, page table entry provides the following information. If valid bit 1, the page is in memory. So, use physical page number to construct address. If valid bit is 0, then the page is on disk. Hence, you raise an exception, and in response to the exception, the page would be loaded, and how the page is loaded, how this exception is serviced we have already discussed. The other important aspect of page table operation is that of checking protections. The access rights field indicate allowable access, read only, read write, execute only. So, I can have pages marked no read, no write, but execute. So, I can simply execute the content of the page, but I cannot read value from that page into a register or some other memory location. And typically it supports in hardware multiple protection modes. There are different modes in which a processor operates. We have seen with reference to an example of ARM, I have basically a supervisory mode of operation and a user mode of operation. When a process is operating in user mode, it will have some restricted permissions. It cannot execute instructions located in a page which is protected via supervisory or the kernel domain. So, this separation is done again to ensure protection of the code. You would like the basic operating system or the basic operational code of an embedded appliance to be protected against malicious attack. Because today, say on your cell phone, you can actually receive the code on the fly and actually you can execute them. But you have to protect your cell phone against a kind of a virus attack or any other kind of malicious attack through these on the fly codes that you are downloading and executing. So, this kind of protection mechanism as implemented through this virtual memory becomes critically important. And protection violation fault occurs if process does not have necessary permission and it is trying to access a location which is not really allowed. Now, with regard to this, a primary observation is critical that in majority of embedded systems, you may not really have demand paging, but what you will have definitely is multitasking, and for ensuring protection and organization of the code of multiple tasks into separate logical address space, the virtual memory systems implementation and use of MMU. And that is why it is very critical for embedded system designer to know about virtual memory. Although in many of the cases, they will not be using hard disks as a logical storage space like in a general purpose computer. Next thing, we shall look at how to integrate virtual memory and cache. Because what CPU is generating the logical address. Now, this logical address is being translated by the page table, which is under hardware control of MMU and under software control of operating system. This translation unit is actually generating the physical address. Now, for finding out whether there is a cache hit or miss, this physical address is to be used. And this physical address is what is being generated by the translation unit is the input to the cache controller. Here we have not shown the cache controller, we have just shown the cache. Now, if there is a miss, then there is a load from the main memory to the cache. Okay. Otherwise, you have a hit and you get the data from the cache. Now, this translation process itself, you can understand pretty well, a page which is not in main memory cannot be in cache. So, whenever there is a fault, page fault, so page fault has to be serviced, and then only when the process gets resumed, it may access a location. So, what will happen in that case? There will be a case of a cold miss for the cache. Okay, so, that data will not be in cache. So, that has to be loaded from main memory into the cache, and you may have the data streaming, that data flowing into the CPU. I am referring to data, but it will be true as well for the instructions. So, what we say is that caches are physically addressed. Majority of the caches are really physically addressed. So, you access by physical addresses. It allows multiple processes to have blocks in cache at the same time. It also allows multiple processes to share pages. And cache does not need to be concerned with protection issues, because these protection issues are taken care of at the level of translation process itself. So, here the organization is when you are using the physical addresses and physical addresses for accessing the cache. But what you can realize is that where will be the page tables really stored? Because when I am using the translation, you have to access the page tables. Otherwise, you cannot do the translation from logical address to the physical address. Typically, page table would be somewhere in the main memory. MMU cannot really store the page table. So, an access to each location therefore implies what? Access to main memory. Then you are actually defeating in that case the basic purpose of using cache. So, there has to be some architectural innovation to overcome this problem. So, how is this problem overcome? So, you perform address translation before cache lookup. So, what you need to do therefore, make the page table entries cached. Okay? So, what we are telling that since this lookup involved memory access, so it is no longer efficient. So, make page table entries cached. So, you have the concept of what is called translation look aside buffer or TLB. So, TLB is typically a small hardware cache in MMU. TLB can also be in L1 cache as well, but in many cases it is a hardware cache within MMU, that is your memory management unit. So, which maps virtual page numbers to physical page numbers and contains complete page table entries for small number of pages. So, there has to be a caching policy for these pages as well. So, now what we have got? CPU generates the virtual address. So, you have got a TLB, translation look aside buffer. Now, if there is a miss for this, there can be miss because I may not have the complete page table loaded. So, if there is a miss, then I have to get that data either through from the cache, okay, or I have to get that information from the main memory. So, I may have part of the page table stored in the cache and remaining part may be stored in this TLB, and then I do the translation. So, once I look at the TLB, okay, I know the information. So, TLB is what? TLB is nothing but a page table entry put into cache. So, using that information, you have to go through the process of physical address generation, cache access, heat and so on and so forth. Now, this miss you should understand has got two kind of significance. One is a page table content itself can be missing from the cache, else it can be actually entry in the page table missing because that block has not been loaded as of yet. Okay. So, why these two kinds of miss may come in, we shall understand gradually. First, let us look at the basic translation process. So, now your virtual page number is referred to TLB. So, TLB is like a cache. So, it will use the tag, okay, in fact tag part from the virtual page number to check whether the tag matches or not. Okay, if the tag matches, then there is a TLB hit and you get the physical page number. Okay. So, now I may not have all these pages, information about all virtual pages stored in the TLB. So, there will be a miss. Okay. And even if I stored them, you can understand the other logical situation is what? the physical page may not be allocated. Okay, so that's also that's case of a page fault. Now the system can follow a policy that it stored only in the TLB information about those pages which are currently memory resident. Okay, so if I am accessing a page which is not in the memory resident, there will be a TLB miss, then I shall go back to the physical memory to get the remaining part of the page table to find out whether the page is really memory resident or not and generate a page fault. So, this is the two aspects that we are referring to, that in this case I have got a TLB hit. If it is a TLB hit, I get the physical page number, I get the physical address, use that physical address to check whether that location is in the cache. So, if it is a cache hit, then you execute, otherwise you have to load the data onto the cache and then only you can execute. In fact, when my memory addressing capability increases, you can realize that my page table itself can become pretty large. Okay. So, if I have given, let us look at this example, 4 KB page size, okay, 32-bit address space, and you have got 4 byte entry, page table entry, 4 bytes length. So, you need a 4 MB page table, which is difficult to manage, and I cannot definitely have maybe a 4 MB page table in translation look-aside buffer. So, what you do? You have multi-level page tables. Okay. So, you have got this one page table. So, level 1 table may have 1024 entries, each of which points to a level 2 page table, and level 2 table has got 1024 entries, each of which points to an actual page. So, in the TLB, you actually put in level 1 table, and maybe if you can accommodate one of these level 2 tables, okay, when it is really a case of multi-level page tables. In fact, majority of the systems, if they are really implementing virtual memory, they would need to implement multi-level page tables. So, ARM core comes with MMU to support virtual memory, and the primary motivation for providing this kind of MMU capability is not only to have demand paging, but most importantly to implement protection. So, like any other MMU, ARM MMU also translates obviously virtual address into physical address, controls memory access permission, determines behavior of the cache and write buffer for each page in memory. When MMU is disabled, all virtual addresses map one to one to the same physical address. That means, for a simpler system, you have a provision to disable MMU. So, your 32-bit addresses which ARM generates will be mapped onto directly physical addresses, and MMU will abort on translation, permission and domain faults. So, these are the exceptions that MMU would generate under error conditions. So, configuration and control components in the MMU are obviously the page tables, the TLB, domains and access permissions. So, here you have got a concept of domains which used in ARM to define the permissions. Caches and write buffers, how they are to be configured. Then CP15, this is, I told you, that system control coprocessor that manages again the MMU, it provides a management interface to the MMU. And there is also additional hardware or extensions of this architecture which provides for first context switch. What is context switch? When I switch from one process to another process, obviously you can understand that a lot of things have to be saved and lot of things are needed to be loaded onto the registers. The simplest thing is that page table definitions have to be loaded. So, that introduces an overhead. Because of these, we may need to have a hardware support, particularly when we are talking about embedded applications. Why? Because any interrupt actually would cause context switch. So, if I do not have a support for context switch, then interrupt latency would be more. So, there are hardware supports in some of the architectures which enables fast context switch. That is, when your virtual memory is implemented with MMU, you require fast context switch provisions, so that the overhead of loading the page tables, ensuring consistency of the cache is taken care of. In fact, ARM MMU supports multi-level page table, because you can realize that it has got 2 to the power 32 addressable locations. It has got 2 levels, we call them L1, level 1 and L2. The master L1 page table divides the 4 GB space into 1 MB sections. An L2 page table can support 1 KB, 4 KB or 64 KB pages. So, different processes can use actually different size pages depending on the way L2 page table is configured. CP15 C2 register holds a translation table base address, an address pointing to the location of master L1 table in virtual memory. Okay, so, this is the starting point, fine. So, for doing any kind of translation, this base address is absolutely important. So, this base address, I hope you remember I have talked about the starting address of the page table. So, this address is critically important for doing any kind of translation tasks, and this is stored in the register of your coprocessor 15. Translation look aside buffer is the provision for that is in ARM MMU, and like any expected operation, it maps a virtual page to an active page and stores controlled data about restricting access to the page. There is no difference in the functionality other than this part. Some of these ARM architectures, it supports locking translations in the TLB. You remember in the last class, we had discussed the ability of the ARM to lock codes in the cache. The same thing is extended here for the TLB. So, TLB entries can be locked. So, pages or page tables which are very frequently accessed, for them the entries in the TLB would be locked. So, they will not be evicted soon. So, the basic operation is, this is your 32-bit address, this is a logical address, this part is used for defining the logical page number, okay, and then the table has got the physical page number. So, this physical page is added with this offset to get the physical address in an ARM system. So, this is how the complete operation takes place in an ARM TLB. Now, domains are used for defining the access permission. Domains control basic access to virtual memory by isolating one area of memory from another when they are sharing a common virtual map. Okay. In fact, there are 16 different domains that can be assigned to 1 MB sections of virtual memory. So, domains actually defines different kinds of access permissions. So, you can have a region, so that is what we call a 1 MB section, which is defined by the master page table. So, using these 1 MB sections, you can associate different kinds of access permissions, and based on these access permissions, the actual accesses will be permitted. So, in fact, here also you will find that ARM is providing 2 level of access permissions. In fact, at one level there is access permission associated with definition of the domain and getting domains associated with the sections, and there would be also access permissions associated with pages. Now, you have caches and write buffer. So, you can configure whether a particular page will be cached or not, or whether you can have a write buffer associated with the page or not. So what we say that when we have a page, whether it will be cached or not, or whether write buffer for the page be enabled or not. Now these can be done by setting appropriate control conditions in the MMU. So I can have pages, but the page need not be really cached. In fact, this is reflection of the same condition that I had discussed in the last class, that some of the pages cannot be really cached. Now let us see how you will be using a virtual system, typically in a kind of an embedded application, for implementation of a static multitasking system running concurrent tasks. So in an embedded system, it is normally not expected you will be having a dynamic multitasking system, that is tasks being generated dynamically, other than computer like embedded systems like your PDAs. Okay. In most of the cases, in many of the dedicated systems, there will be a set of fixed tasks which need to run concurrently. Tasks can have overlapping virtual memory map. In fact, they can have same or identical virtual map, but they will be located in physical memory at addresses that do not overlap. It may also overlap when they share pages. When they share common pages, that may also overlap. Then you configure your domain access and permissions in the page table to protect the system. So each task will have associated with it a domain access, and that will restrict the access rights to the pages belonging to the task. And demand paging is not necessarily implemented. So during context switch, different page tables is activated. So it will switch from one page table to another page table, because virtual to physical mapping change. And to ensure cache coherency, caches may need cleaning and flushing, because I may not like the entries in the cache to remain, because they can be removed and flushed at one go. Flushing would be effectively removing the contents at one go. TLB will also need flushing, because I am now using different pages. So this is the basic overhead for context switching. And in fact, when we have context switching hardware, first context switching extension in ARM, you have the hardware support to do these things fast. So reduced the time for context switching. So another policy which is implemented is write through cache policy. So in this case, data cache is configured as write through, will not require cleaning of data cache. Why? Because I can simply forget about the contents of this data cache, because for every write to the data cache, I am writing back to the memory, but obviously it has got the drawback in terms of additional time consumed for writing into the main memory. When you use demand paging, you use in many cases, in the majority of the cases for embedded system, flash memory as non-volatile source. In fact, you have disk or file systems actually implemented on flash memory, and you have programs which are stored in the flash. Typically your OS will be stored in the flash, and you copy from flash to RAM during execution for faster access. So under those conditions, you can use dynamic paging with loading pages on demand. So under those conditions, you typically adopt write back policy for the pages, because access time to flash is much more compared to RAM. So you won't like write through policy to be implemented for the pages. Now this we are talking about the write back or write through policy of the pages and not of cache blocks. Please keep that in mind. So if you are using a NAND flash is that flash which has got very dense storage. It can have fast burst mode access, but its random mode access is not that efficient like your NOR flash. So if you are really using NAND flash because of its density of storage, then what you can really use is demand paging. So in your NAND flash, you have the OS, you have the code for applications, application 1, application 2, you have the complete file system, and you have this MMU sitting with a microcontroller like your ARM MMU, and When you start up the system, actually OS gets loaded onto your SDRAM. In fact, these pages can actually be locked so that they are never moved out of your SDRAM. Then depending on the application requirements, pages of the application gets loaded onto SDRAM, and for running that application you would need stack and heap. That pages also could be accommodated in the SDRAM. So, the pages gets loaded on demand on the SDRAM from the NAND file system. So, this is an example where you can use demand paging in embedded appliance. But when you are using NAND flash, then your page replacement policy may need some modification, because we know that LRU is the most commonly used policy. What is that? Least recently used page to be replaced when we do not have enough pages in the physical memory. With NAND flash, a different policy is followed, because write cost for an evicting page is higher, because you are writing onto the flash. So, keep dirty pages as long as possible. Okay? So, you modify the policy and say that you evict least recently used clean pages first and then dirty pages. Okay? So, you reduce the overhead of write back. Okay? So, you can see that in the context of embedded systems, all these well known policies also undergo change. And why LRU is a decent policy? Because if it is least recently accessed, that means it will not be accessed in future because of the principle of temporal locality and spatial locality. This finishes our study of memory systems in embedded system. We have examined cache and virtual memory organization. We have also understood the functional role of MMU and cache controller. We shall look into other aspects of embedded system hardware, particularly the bus definition, in next few lectures.